I'd like to welcome everyone today to our webinar. Today's webinar topic is CrystalStream wants to apply for your projects, a review of our product resume. For those of you that don't know, my name's Jeff Benty. I'll be your moderator for today's session. Should you have any questions, you can feel free to message me privately, and or if you're having any technical issues, we'll try to get them addressed. Throughout the session, feel free to ask your questions during the session, or at the end we will open the floor to a question-answer period, and can kind of try to address any of your questions. Keep an eye on your chat windows because we will type email addresses and other pertinent information in there, so please pay attention. With that, I'd like to have everyone join me in welcoming John Mall. John is our speaker for today's session. John received his education from Florida State University. Over the years, John's gained invaluable environmental experience while working in the mining and landfill industry across the country and later owning his own civil engineering firm. John, in conjunction with Clark Hughes, are the inventors and owners of the CrystalStream Technologies product. John currently operates as CEO and oversees and directs all research, development, and engineering services for CrystalStream. John played a critical role in being a founder of the Stormwater Equipment Manufacturers Association, or SWEMA for short. So he's been very active in our industry. With that, I'd like to ask everybody to join me in welcoming John. John, the floor is yours.
Thank you, Jeff. Folks, I appreciate you all coming today. This is a little bit different webinar than I normally do. It's more product oriented, and as I was putting this together, I decided that it still needs to be a learning session on some principles of water quality. So I'm going to make some side comments about how we address some of the things that I'll bring up today and hear about water quality. So for those of you who are used to hearing science only, this is going to be a little bit of a CrystalStream commercial, but I hope you will bear with us on that, because we certainly do want to cover what a BMP should be able to do. So with that being said, engineers and other site designers, site design professionals, are trying to find a BMP that meets the requirement of their jurisdiction. I put in parentheses, and it actually works. Those two things are not always the same. I know when I give a presentation to engineers, the one word that's in the back of their mind is, that sounds great, but can I get a permit with your device in my jurisdiction? Because otherwise we're all just wasting our time. So as this industry started to develop, I came in the industry in 1999. I had used some of the competitors' products at that point, and I wasn't really satisfied with them because they went ahead of water quality ponds. And I saw a lot of trash and a lot of debris and a lot of sediment, and was wondering how these things work. So back then and at one time, and still today in some places, the literature of proprietary manufactured by BMPs was more or less accepted as the gospel, because everyone was looking for something that they could get on the plans. There was kind of a panic of trying to do water quality, and the states wanted to have their permit from their EPA region, and the cities wanted to get permitted by the state general permit. So this is still actually true for public domain manufactured BMPs. And when I say that, very seldom do you get to have a natural thing, an existing lake or an existing wetland, and use it as a BMP. In fact, you're prohibited from discharging pollutants into those things. So everything is manufactured. Some of it is made of sand and concrete, but ponds and sand filters and infiltration systems are all man-made. And in the manual, they remove 80% of TSS on every site every time. In fact, you use them, you design them according to the manual, you get full credit. Well, over time, as claims of magic removal rates became more prevalent for the manufactured devices, people said, you know, I'd sure like to see some testing that back that up. It's kind of interesting that today testing still doesn't exist for most of the public domain systems. But that's another axe to grind. Let's talk about, if you're going to use a water quality manufactured a proprietary system, how do you get it approved? Well, to start out with, the definition of water quality treatment is usually pretty sketchy. It's very nebulous. And the reason it is because if you're actually going to test for, let's say, heavy metals, or if you want to try to get a particle size definition of what's suspended in the water at different flows, or you need to know about phosphorus or nitrogen or some other particular constituent, it's very expensive. In fact, that's the largest part of most testing regimens is the laboratory bills for analysis. So the EPA in their guidance and management measure 5, which at the bottom of the screen you can see how to get to these this management measures. Very interesting, by the way, that most people do not read them and don't understand them. So the conclusion was, well, it's expensive to test, so if you just test for suspended solids and get out 80%, you should be good. But then you do that on a water quality storm that is locally defined because climate varies in different areas of the country. And then the rationale goes, well, everything important washes off in small rainfall events. So you see things like catch the 1-inch first flush. Well, that's nice for a volume. Everybody knows that 1 acre inch is 3,630 cubic feet, but what about flows? Does the 1-inch fall in 5 minutes, or does it fall in a full day? Now the difference in that is 12 inches per hour in 5 minutes, 4/100ths of an inch per hour if you're talking about an all-day storm. So it can be a huge order of magnitude in the actual flow. So remember that removing solids is only a surrogate for removing the pollutants found in stormwater runoff. There's nothing especially obnoxious about clean sand, although too much sand and sediments in a stream can choke it out, obviously. And too many fine sediments can coat biotics and cause all sorts of problems. But removing the solids is really just a surrogate. And 80% removal is federal guidance. It's not a mandate. It's not in their law anywhere. And there's very different methods and assumptions are used to prove 80% of removal. Really, in the field, until you know what you missed, you can't really prove what you removed. You could show that concentrations at a certain number of times during the storms were 80% better downstream. But you're not going to really know what percentage of removal you had in the field without knowing what you missed. Well, all testing is not created equal. There are people that have tests. I can think of one where we have a device that we feel certain can remove about 80% of a normal mix of particles at about 1 cubic foot per second. Well, there's a competitor that has essentially the same size device, but theirs can do it at 9 cubic feet per second. That's interesting. When they were actually tested by a third party, their number came up 1 also. But third-party testing is not hiring someone to test your device. Even if you turn that test into someone who examines it to meet a protocol. Third-party testing, true third-party testing, and you can look this up, but I went to Wiki and some other places because this term has been misused for so long that it's now become third-party testing means there was a third party. Well, if you're a company and you hire a lab, that's 2 parties. It's hard to find out what the third party is in this equation. The third party or third-party testing, in our case, for example, and in the case of many of my competitors that were tested under the ETV program by the USEPA, the third party was the EPA. Second party was the laboratory. So we were tested. The EPA took our device away from us, locked it down literally, and did with others too. Had a lab, had a test operator, maybe they're the fourth party, operate the test, send the results, send the samples to a lab. The lab reported the results, and then these results were analyzed by the NSF, which is a testing company that specializes in water pipe testing and all sorts of things. And then the EPA wrote the report, good, bad, or ugly. If you look at the ETV studies, you can find one device, for example, that would not run as fast as they said it would. They couldn't get the water through it, so it got I guess a 0. It didn't really get a conclusion because they never could get samples out the other end at the water quality speed. And the results range all over the place. But a third-party testing is the gold standard. I don't know how we've arranged this, but we have had the good fortune to be third-party tested 4 times, and all the tests were good. Second-party testing is usually conducted to a particular standard, like the TARP program, TARP Tier 2. You have to bring a test plan to NJDEP. NJCAT administers this for them. The test plan is approved, and then the test plan is executed, properly witnessed, etc., by others in the field. And then you have the lab results analyzed. All of this is paid for by the manufacturer and then sent back to New Jersey for verification of the results. Did you follow the plan? And then the report is written. If you get a poor result on this kind of a second-party test, and I've seen these tests, you certainly don't send it back for approval. If you ended up at 30% removal, you would probably increase the size of your device or change the design of your device, and the idea is to get something that can be verified. But that's a second-party test. Now, believe it or not, there's a lot of self-testing out there where the manufacturer sets up his testing, and if we had half a day, I could tell you lots of great ways to get good results out of self-testing, including using a protocol that's favorable to your product to start with an assumption that we're going to test it this way. So the invaluable third-party testing is wonderful, but you got to understand you can't force somebody to have it. If the resume, and we're talking today about what's the resume of your product, if the resume of your product does not include third-party testing, it's difficult to say you got to do it because you can't buy it. You can't buy it. Someone has to volunteer to take an interest in your device and test it. Second-party testing is good, but when their protocols vary, when I say a protocol, how fast is the machine going to be run relative to the water quality speed? There's a performance curve that comes out. How do you evaluate that curve? Do you count the 1/4 water quality speed that's 50% since most of the storms are down in that range, and then higher speeds at a lesser percentage to get an average mimicking the storm pattern? What size particles do you use? What concentration do you use? There's some protocols that specify field testing only. Some protocols that specify lab testing only. So, and plus, if you look at the pond down here at the bottom, most land-based BMPs just can't be tested because you can't control the concentration coming to them, and you can't control the flow coming to them. So, for field testing, they have what's an acceptable storm. Some storms are too small to fill the pipe deep enough for a sample to work. Other storms are too violent for the equipment to get a dependable reading. How do you sample? Where do you put a sample probe? There's just a ton of differences, even storm to storm within a single test on a single device. We found anomalies where test operators would move the sample probe because it was getting too much backflow from downstream or whatever. Now, it's hard to say that that's an accurate test, and all these questions come into play. So in lab testing, you have to decide the flow rate, the size and concentration of particles, where you inject. There's a ton that goes along with lab testing too. If you go look at something historical like NJDEP, NJDECAT, TARP, over time, if you read all those tests up there, and they're fixing this over a period here. If you go read, everyone used a different particle size, everyone used a different lab technique. So now they have standardized that, and they're going to phase out their old approvals and phase in some new ones, but then everybody will be literally on the same page. So how do we address this? Jeff mentioned I found the Stormwater Equipment Manufacturers Association. This means me cajoling and bribing and whining and yelling, trying to get, it's like herding cats, trying to get a bunch of guys who compete with each other every day and don't like each other so much. We're natural antagonists because we think we all want to promote our own products. but we found we had some shared values, that maintenance was ignored in the real world. Oh, we'll put in a pond, you never have to maintain that, or a sand filter or whatever. The costs for those systems, by the way, are much greater than manufactured systems. But that was one place where we knew the cost of our system was less. But when you go read the manual, still today, manufactured systems may be effective, but they're very high maintenance. Just not true. So we had to try to clarify that, educate people some. We wanted good protocols, because I'll tell you the truth, it's a joy and a delight to compete in a jurisdiction that enforces their protocols and everybody's on a level playing field. All of us were not afraid of regulations, not afraid of protocols. We also wanted to point out that most of the standard practices had never been tested. You could measure the water coming out of their practices and the water coming out of our products, and our water was better. And as manufacturers, we all want to be treated equally and fairly, and we want to promote water quality. And so there was a lot to bind us together, even though there's still a lot that divides us on how we size our devices and how we want to compete in the marketplace. As you can imagine, there's always a pressure to substitute a product that's smaller or costs less, and at the time the dollars have to be spent, owners and contractors and even sometimes jurisdictions aren't quite so attentive to performance. So in 2009, we petitioned the NJDEP to correct, I say large variations, I'm being kind there, to correct huge inequities in their protocol that had changed over time. The older products were approved as the same as the newer products, with much tougher standards for the newer products. Plus, lab testing is good for 50% no matter what you get. You could get 99% of the particles on the lab testing, you're still 50% until you do field testing. To the great surprise of SWEMA, we were asked to actually participate in that. New lab standards are coming out. I think Jeff could tell you the number, but I don't have it in front of me, but the work of the C2770 committee and the ASTM organization has produced a laboratory testing standard protocol. And ASTM is a very tough group to work through. It takes a long time because these tests have to be repeatable. You can't have variables that would give different results. It's a standard, just like the standard for the compressive strength of concrete. You have to be able to depend on it, literally build a building and depend on it. The test must give the correct answers. And so that ASTM committee and SWEMA committee, a lot of the guys crossed over. And these efforts that have been made solve some of the basic problems with BMP testing. But there's two big things you still have to think about when you're considering the resume of a product. Whatever is gotten in the lab, I've seen this, I could name you a bunch of places. South Carolina DOT, for example, the city of Knoxville says, hey, tell me the speed where you got out 80% of this sediment and you're good. And unfortunately, laboratory conditions are nothing like field conditions. In the laboratory, you run at a constant speed, you run with a known particle size distribution that doesn't change, and you run at with a constant concentration. They are very careful to get all that steady. In the field, particle size distribution changes from moment to moment, flows certainly aren't steady, and concentrations certainly aren't steady. The same storm 2 days in a row will have completely different characteristics of how it carries off particles because of the particles that were subtracted or washed off during the first storm from the surface. Both of these are very expensive, and while I've been approved in literally hundreds of jurisdictions based on my federal ETV testing, that was one model of my device in one time under one protocol in one place in one set of 15 storms. Good that I got a great score. We're used to getting good scores here on our test because our device functions and works, and we understand and we're confident when we go into a test that that's going to be true. But how do you then take my one device that was tested in Griffin, Georgia by the EPA and project that 10 by 5 device down to my 4 by 6 device I call it a model 646, or to my 9x5, or all the way up to my 24x6. How do you do that? I've been fortunate that I've had the 10-foot device tested in the field, a 9-foot device tested in the lab, a 9-foot device tested in the field, and then, a 12-foot device tested in the field, and then now a 20x6 device tested in the field. So I've had all the way through my product line tested. I don't have any device except for my smallest 6x4, which, by the way, when we average how they perform in the field, is about one of my best performing devices. So we, dollar for dollar or size for size. So we know they're not similar. We know things change. And one of the big things is that silicon, the sand we test with in the laboratory, has a density of 2.65. That means it is 2.65 times as dense as water. With air not being able to materially affect a bowling ball and a BB, we had experiments done that we came up with the law of gravity, that things fall the same speed through a gravity field. Well, a feather doesn't, because of the density of the air versus the surface area of the feather. Well, in water, it's the density of the particles up to a point that governs how fast they fall based on the density of the water. And unfortunately, the materials we find in nature average about 1.7 times as heavy as water, not 2.65. So whatever happens in the lab is certainly not going to apply there. But if you remember, that density is an average. If you think about materials like vegetative materials, some of them have a density less than that of water. They float. Some of them, vegetative materials, once they have decomposed, have a density almost equal that of water. It takes them a long time to settle out. And then we have wheel weights, and we have plastics and other things that some of them are heavier, some of them are lighter, but the overall average is 1.7. Oil, of course, floats, gasoline, those sort of things. So the lab conditions really don't relate very well to what we actually see in the field, but there is an important thing. If you test 3 different devices of the same size, claimed size, let's say by the manufacturer, they're 1 CFS device, you can look at their performance curves in the lab, and you can make a decision as to who is the most efficient. You're going to find something very interesting. Some of the designs excel at larger particles, and some excel at smaller particles. And it's not exactly linear like you would think, oh, well, the bigger device is going to do better on smaller particles. It doesn't exactly work that way. All of these things have different shapes, and they respond differently to the hydraulics. Well, one of the things that it's interesting, I don't know if any of you saw my presentation on a microscopic view of materials, but lab materials aren't similar to what we find in the field. This slide shows up on the upper left OK110, and at the bottom Silcasil 106, which is a crushed silica, test silica. These 2 products are provided as test materials because they're very consistent. OK110 is now being phased out, but they are very dependable, so you know what you're getting when you buy several tons of it to test the system. By the way, it takes tons and tons to test the system. Versus what you see in the field with a very wide range of particle sizes, angular as opposed to rounded. OK110 is rounded, Silcasil 106 is mostly angular because it's crushed, fractures according to the crystalline patterns of quartz. And all sorts of organics can come in. The CrystalStream product takes this into account because we designed to catch the highest volume of sediments we can. Some products are made to catch tinier particles. Actually, it turns out we catch as much of the tiny particles as them. But they then bypass and they miss a lot of particles, including the larger particles. We designed at the true makeup of field particles. And we designed for the density that was out in the field. So we have a 3-step process. You're not going to be able to sink floating materials and organics, so we screen them out on the way in. you're not going to be able to capture neutrally buoyant organic material, so we filter it out through 3/4 inches of coconut fiber on the way out, which also tends to capture a lot of small particles. If you look at the lower right slide there, you can see the small particles attached. That happens to be a pine needle at pretty large magnification. And you can see small particles all over it. And this is what we find, that the small particles don't live in a vacuum. They like to attach to stuff. So, why do the laboratory testing? Remember, it gives us a very good basis for comparison of technologies. Now, when I did my laboratory testing, I was required to by one city. They didn't even really have a protocol. It's one sentence that said, use OK110 and get an analysis of the performance at various speeds. But what I wanted to find out, and what I told Jim Malo at Alden Labs when I went up there, I wanted to run it from 0 to 100 miles an hour. I wanted him to break the parts out of my device by pushing water through it in excess of the 25-year flow. I was happy to see that in excess of the 25-year flow, we were splashing water out the top of the vault. The parts survived. In fact, they survived intact. There was no damage. But see, you can't know that. People talk about what they know about their device. Very few people have ever seen their device running. You can't get in it during a 25-year storm. Almost all of this is supposition or assumptions that they make, or they just make their device bypass. Just so you know, as a group, I'll show you in a minute, but our devices that bypass catch about 1/5 of what our devices that stay online the whole time. Well, it depends, 1/5 to 20 to 40%. So we know that bypassing as an overall strategy, remember we're dealing with floating, neutrally buoyant, some extra heavy stuff. As an overall strategy, not very good. If you want to be absolutely sure that you don't have to study your device in a 25-year test or worry about resuspension, yeah, bypass. It's a great thing. In our case, it just means an extra 3,000 or 4,000 pounds of stuff goes downstream, and we know that's true in everybody's case. So the laboratory testing shows your hydraulic limits of your technology. When do you get into turbulent flow? And when should you think about a bypass or an internal bypass, or are there other aspects that hurt your performance? Our devices had a deeper pool than we thought while they were running. And we had to work with the fluid dynamic experts up there. We were using a circular orifice equation. And it turned out there are some other things that steal performance in a sump device, which was very interesting to learn. That helped us in our design. So you learn a lot in lab testing. And finally, if you have a controversial method of scaling, and there are some people that do, they claim they can make their device deeper and it'll work better. If you make it deeper, the water does stay in longer, but the particles have further to fall. And according to Dr. Gary Minton, that's pretty much like chasing your tail as a dog. You can't catch up by adding resonance time, but increasing depth so the particles have further to go to the bed. And that's not totally accurate. There are other aspects. But HLR, hydraulic loading rate, does dominate how these things are done. But if you do want to take a different approach, you could test 3 different sizes of your device in the lab and verify how you scale. And it can change based on the shape of the device. So if you know the field conditions, particle size, flow, site geometry, laboratory testing can be very good at predicting the overall suitability of a device. For example, in Florida, if you know the size of the sands and the low amount of the low amount of fines that you have, clay and silts, and the organics you have, you could probably do a pretty good prediction of the performance. So this scaling problem, how you know one device to another, let me say we use hydraulic loading rate on all of our devices. Our devices were tested at 31 gallons a minute per square foot. We got a removal rate of 89% with the EPA and 96% with the Clean Water Management Trust Fund. People didn't like either of those tests. They didn't like that they used SSC in the EPA test. EPA depends on that. They verified it, but so the TSS test is usually more strict. We got a better score there. But how do you test a small thing? And that's what almost everybody does. And the scaling doesn't work out. If you test your smallest device, it's tempting to do that. in the lab or in the field because it's cheap. It's a small amount of materials, lot slower water speeds, makes things easier. But this has been projected up. If you'll notice, if you go back and look at, well, NJCAT's a good example. They accepted manufacturer scaling claims for the longest time, and now they've gone back and go, you know what, you can't prove this, we can't prove it, we don't see it in the field, and they put everybody back on the hydraulic loading rate and said this is the way it's going to be. Everyone, of course, has the opportunity to do further testing and prove their scaling. But right now, a lot of people went from a treatment rate of, say, 10 CFS to 2 on their biggest devices. Now, financial realities, I'm not picking on people, but it does limit testing, especially field testing. Again, we are so fortunate to have what we've got. Until recently, when almost every agency out there has gone to hydraulic loading rate, there wasn't a published standard for scaling one model up or down. So hydraulic loading rate is what's, surface loading is what's used in most cases. Some people have volumetric scaling, but so far no one's really stepped forward with that. So I'm not going to spend a lot of time here on scaling, but if you want to get a copy of this webinar, essentially this will explain the scaling. It would say a 2x2 device has 4 square foot, and a 4x4 has 16 square foot, so it could flow at 4 times the rate, all other things being equal. They call that N factor on scaling, the factor of 2. U square, the U square feet. If you use volumetric scaling, a 2x2x2 would have 8 cubic feet, a 4x4 would have 64 cubic feet, which means it is 16 times bigger. This does not work that way in the field. If so, you could do a 1 foot by 1 foot model, 100 feet deep, essentially auger a hole in the ground. It'd be the most efficient water quality device in the world, but that's not how things work. So laboratory curves are not straight lines, but if you look at the laboratory performance curves, you'll see there's a straight section in the middle. And the reason they're not straight lines is there's a point where laboratory, any device running slow enough gets everything. And going real fast, it begins to resuspend, so what it can get out stabilizes. But HLR overlays these curves much better than exponential curving scaling does. And making the device, as I said earlier, twice as deep means it has to fall twice as far, which means it has to stay in twice as long. So your resident time increased by volumetric scaling is tough. I will say this, if you add volume by putting a protected sump in your device, as some products do, that advantage of limiting resuspension is a real advantage. It's something that can be proven and can be shown. It might not improve the performance of the device from a capture standpoint, but it certainly improves the performance in that what it captures is not going to go back downstream. SCDOT, December 2011, decided that they were going to adopt an HLR-based specification for water quality devices. They want them at 20 gallons a minute per square foot to be acceptable. They will allow you to go up to 26 if you can prove it. And what we had happening in South Carolina, by the way, unfortunately has happened even after the spec was issued. Someone can come with a 4-foot round device and some voodoo testing and say, well, this can replace a 12x6 rectangular vault because HLR doesn't apply to us. Not true, and certainly not acceptable, and not provable by anyone. So in New Jersey in 2011, as I mentioned earlier, they said, okay, we're going to use, you have to use the HLR of your untested models. And if you go look before and after, some manufacturers changed nothing. So I would say their resume remained constant. What they could do, they still can do. Others had tremendous decreases in their larger devices because no one had ever proven they would work at those speeds. In fact, field data indicated otherwise. So HLR is probably the way to go. If the resume of your product does not include a dependence on HLR, I would ask for comparative lab testing to show, to clearly demonstrate that it defies the laws of gravity or that it has something that would prove to you that it works in a way different than what I would call the laws of physics would dictate. It'd be nice if all the manufacturers would stick to their testing and rules. But companies, a lot of companies, and I don't mind saying this, they will have testing, and I've tried to be ecumenical, I've tried to be nice to folks, but I started pointing this out. I would go, well, here's what they say here. Why don't you look at the jurisdictions that strictly make them stick to their testing and see what their speeds are. And it doesn't give you a lot of credibility when you're limited to one CFS in New Jersey and one CFS in California and one CFS in Washington State where they check your testing. But you claim that same device can do 9 CFS in Georgia or Tennessee or somewhere else. More of this needs to happen, and here's why. Everyone wants to depend on testing, and everyone wants to realize that water quality can be accomplished in a small footprint, but you got to prove it. You got to prove it with field results, not necessarily a third-party field test, but you got to prove it. You got to show up every day and do the job. And somebody can have a great resume when they apply for your job, and the CrystalStream product's got a great resume, and so do some others when you look at their brochures, but it's what they do on the job. Whether or not they're willing to stand behind their product, we give a 5-year warranty, that sort of thing. So I actually had a statement made by someone in a competitive job that they don't rely on gravity. We have a swirling technology. HR doesn't apply to us. Well, they had been tested twice, and their testing indicated they could not perform at over 50%, even at 12 gallons a minute per square foot for hydraulic load. It went out 12 gallons per minute, so a really low one. Mid-20s is pretty much what most products can do. So if we're going to do water quality as a company, CrystalStream, for example, we're going to stick to our testing unless we're told not to. Now, we get some jurisdictions that say, hey, we're only interested in 50% removal, you're nothing but pre-treatment. We can design to that. But we also can meet the goal of removing 80% if someone asks us to design that way, and that's the way we want to design, and we want to design that way for 2 reasons. First of all, it lets us stand behind our product. We don't want to overspeed our product. We don't want it discharging materials. We don't want someone downstream of the lake calling up and saying they're finding styrofoam cups and sediment in their lake where CrystalStream is protecting a pipe. And secondly, for the credibility of this industry, for people to believe, there's a place in New York where they do a demo, and I think it's the state DEP that does it, the Department of Environmental Protection. It goes, they show a guy pulling a rabbit out of a hat when they talk about our industry, the manufactured BMP industry, and that needs to stop. That needs to stop. People need to have confidence in what's going on. So when you're checking the resume of your products that you want to put on a drawing, or a contractor calls you up and goes, hey, I found this thing for $9.95 as opposed to the deal. Remember, you can use a lower gauge pipe and a smaller pipe and you'll save money. You can put out less paving and you'll save money. You can use a block wall that doesn't have tiebacks into the slope and save money. Hey, you could not hydroseed or use a wood-back silk fence instead of metal stakes and save money. But that's not always, doesn't always meet the specification. And, you know, when someone says I need a truck, you could get either one of the items above. They're both trucks by anybody's definition, but they're certainly not equal. And the magic guy in our industry, and trust me, when you really want to increase sales, it's tough not to become a magic guy and start making strange claims. What you see on the bottom left is a water quality element that's protected. Happens to be one of our devices, but it could be any one of the people with the proper resume. It's a visual element. It's getting some aeration. It's doing some really good things. And that is not equivalent to most land-based BMPs, and certainly not equivalent to someone who's undersizing a device or whatever. NJDEP has become a standard in, I think, 18 or 19 states. They want to get lab testing. Now they have a good protocol. They want field testing to get a full approval, because you've got to be able to show practicality in the field, maintainability in the field. Something might work well in the lab, but then for an hour, But when it's out there for a year, according to the manufacturer's cleaning specifications, is it going to plug up? Is it going to blind out? Is it going to start to bypass way too early? ETV is a great standard. They used to seek grants, so that the testee never paid for the test. Because of tough times today, the ETV is programmed by the EPA. It's now suggesting that the person getting tested, pays for their test. I think that sullies it a little bit, but if it's true hands-off, you just plunk down the money and go away for 3 years until you get your answer. That probably would be pretty good. The NJDEP lab tests are going to get better, and so these sort of things are coming along. And there's a lot of folks out there selling products in states that require full treatment that only have that 50% efficiency. They'll go, well, I'm Tier 2 certified. Yes, you are at 50% and slower flows than what you got. So check the resume. A simple statement, for example, that I've been ETV verified doesn't mean anything. What are you verified at? I was verified at 89% removal, but you can also get verified at 20% removal, which may sound silly, but it could be useful in some cases. Some of the technologies certainly can be useful based on what they're verified at. This is some example. I put 3 things up here that they tested. Product A tested a 4-foot model, and they got approved at 50% at 1.1 CFS, but when they went to their 12-foot model, they claimed it would treat 30.2. Well, using HLR, that was 10.1. A lot of devices were sold claiming they could treat 30 CFS. And you can look down the way. You'll see a pattern here. The middle one is a little mixed because it's a 2-chamber device, product B. So it claimed 27. It only got reduced to 12. But the real ratio difference is almost always 3 to 1. Almost always 3 to 1. If you like to do math, you can go back at the scaling factor and figure that out pretty quick. If you look at the ratio between the examples I showed you with cubic feet. So scaling is a bigger issue than how you get tested. And when these people test these smaller models and they project up into larger flow, that's how they work. We have a lot of science that's out there. And the statement goes something like, we have enhanced secret magic particle settling using ancient fast fall-swirl hydrodynamics. Our product's bigger on the inside than the outside. Trust me on this one. I've actually heard the phrase secret particle settling techniques used at trade shows. We don't depend on gravity. And one of my competitors walked over to the offending person and said, I guess your product will work in orbit then. So you just have to be careful. Everybody can print a really pretty brochure, but ask the questions and find out what the real deal is. And you can read the bottom one if you want. I've heard more pseudoscience thrown out about products, including the frisbar coriolus effect. Actually, there is a benefit to using magic design techniques. You certainly reduce maintenance costs because you're not going to catch much. So some takeaways from what I've said today, and I'm going to relate it back to our product here because this is supposed to be an exposure of product. Remember, laboratory test protocols are becoming standard. And if you look at those performance curves, they are almost all exactly the same. You can look at the bottom and change the flow to hydraulic loading rate based on the size of the device, and the curves almost always overlay. There are gaps in the efficiency based on the shapes, but really there's no magic in settling particles. In fact, we've been doing it in wastewater treatment forever. Surface loading is an absolutely known and proven way if you watch your velocities to keep particles separated and capture them. Testing all models enough to provide sufficient field or lab data is not something that anyone can afford. And some BMPs, like the field ones, the land-based, can't be tested at all. So don't expect, I went to Wisconsin, I believe, and they looked at my testing and they said, okay, you're approved for that one, your 10-footer, but not the 9, not the 6, not the 12, and you need to go get the EPA to test all those for you too, which just wasn't feasible. So, but scaling is the most critical issue, and it's now being addressed, and it's being addressed using surface loading in most jurisdictions. We always scale by HLR. We average 18 gallons a minute per square foot. We'd like to keep it to a maximum of 26. That there's a little caveat there. If you decide that your water quality flow is the 2-inch first flush, and your neighboring state's water quality flow is the 1-inch first flush, and we were designing for the 2 states, we would have a discussion with that state jurisdiction and say, you know, your rainfall, and we'd show you the charts are the same for both states. If I design to an HLR of 26 in state A, the guy with the 1-inch, and you're in state B, and I designed a 26, this device is going to be twice as big. And I can tell you right now, I could make it the same as the other state, not twice as big, and it'll work just as well. So there's some things that can affect what we would call a standard maximum of 26 gallons per minute per square foot. That's why we have PEs on staff. That's why we vet all the rainfall records, and that's why we have a discussion with both the jurisdiction and the engineer. And you should not be too surprised that we have the best field testing on record. Every single time we're in a, I will say this, in the USGS test, someone did beat us just a little bit in what they would say a vitamin concentration and some loads analysis on TSS. If you look at the raw data, we were pretty close, but I'll have to credit them for being right up there with us. We killed them in nutrients. We killed them in metals. We killed them in fecal coliform. But I gotta give them credit. But that's the only time our device. And by the way, it wasn't a side-by-side test either. They were on a different catchment, and they had different particle sizes. But fair is fair. They got a better TSS test than us, but no one else ever has ever. And consistently through our field testing, we've got the best records of anyone. So this is our resume. We were tested by the EPA. I was told by a gentleman the other day he didn't care what the EPA thought. He knew a whole bunch more about testing than they did, and that's fine. I had to write that jurisdiction off. We've been tested and verified to remove 89% of TSS using ASTM D-3977-97, which is the analysis method of choice for stormwater. I could say a lot of things about that, but I will just tell you it's what NJDEP uses, it's what every single lab uses because it's repeatable and accurate. We were also shown to use 40% of phosphorus. Some people, I could name names here of counties and states, we don't like ASTM D-3977-97. We want EPA 160.2 because it favors small particles. Now, why they want the wrong answer and a non-repeatable test, I don't know, but we were tested by the Clean Water Management Trust Fund and found to remove 96% of the TSS using their favored test. I say their favorite test, the folks that don't really know. And to be honest, 96% is a big number. The inaccuracy of EPA 160.2 cuts both ways. So I tend to think 85 to 89, 90% is about what we do. I don't think we get 96% of TSS. But we've got a certified test that says that, and that's a good thing. And they also found we got 74% of both phosphorus and nitrogen, which is better than the 40. 40% is all we've ever claimed. I think in the USGS test we got 39. Consistently, when phosphorus has been tested, we're around 40%. 74 is great. Could be that this was a high particulate phosphorus area, and since we captured particulate really well, that could have been what boosted us up there, but it's still a good thing. These tests were paid for and conducted by others with no participation by CST. Literally locked down our product, tested it, and told us what it did. We didn't hire anybody in there or spend a penny. We have over 7,000 field maintenance operations showing performance beyond any loading models of real materials. Example, most models say the wash-off rate is, now today they say it's 200 to 250 milligrams per liter, which everybody has on the tip of their tongue. They know how to convert that with 40 inches of annual rainfall into pounds. I'll help you out here. The EPA said it was 69 milligrams per liter average on commercial sites to 113 on residential sites. And a long story made short, they're talking 800 to 1,100 pounds per acre per year, where we have all these thousands of devices out here, and we have 7,000 maintenance operations, and we have found that number to be closer to 5,000 pounds per acre per year, which is implied average concentration of over 400 milligrams per liter, meaning some storms, and you can see these storms. Go look at our EPA report. Go look at USGS test. Some storms deliver solids at 4, 5, 6, 700 milligrams per liter. Nothing like what we do in the field, in the laboratory. So we've got the 7,000 maintenance operations. Our first device is still in service. We've removed 50,000 pounds of material from it. We keep records. We pay attention. We see our good side and we see our bad side. Continuing our resume, we do all the calculation for sizing and relate them directly to our testing. You will not find a specification for a CrystalStream that doesn't talk about our ETV testing, what our hydraulic loading rate was, and what we recommend for that area. Generally, 26 gallons a minute square foot. Generally, we are below that. Almost always we are below that. But we provide those calculations, including vertical velocities in the unit, horizontal velocities, and things that real engineering geeks can get their teeth into. But we do that so that no one's picking our device off of a chart or using a CD with a program to size it. And I've seen this over and over again. A guy goes, oh my gosh, we can't afford that big 12-foot round model. So they change the particle size distribution until they get the model they want. Not good practice. And so we also service what we sell. One of the goals of the CrystalStream when we invented it was nothing proprietary, nothing fiberglass, nothing shaped, no plungers, no cases, no covers, no anything that you can't get anywhere except from us, because hopefully, I would like to think the company's immortal, but we all know it's not. Times change, water quality will change, the way we do things. We may all move underground, who knows. But it's wrong, in my mind, to put out something that a property depends on, or jurisdiction depends on, that you can only buy replacement parts or only get the canisters renewed by Joe XYZ company. We are expanded aluminum, which is everywhere. You can buy at any city USA aluminum plate, perforated aluminum, along with concrete, and some coconut fiber, which you usually can get at your nearby big box store. We screen, separate, and filter in all cases. Most folks just separate, a few screen. They don't have a lot of variability to that screening. We have to change based on the site, obviously. And we use the coconut fiber filter unless we're prohibited. We provide a 5-year warranty to all owners if the devices are cleaned on schedule. We can't give a warranty if they're not going to clean them, because they are a very efficient sediment trap. We have seen these things go 3 years and not be cleaned and have 5 foot of sediment in a 6-foot device, and the device still be holding material, obviously. It's not made to do that, but we give that 5-year warranty so that when somebody gets it, they know we are going to take care of it and we're going to fix it if something breaks. It's effectively a lifetime warranty for people that actually hire our company to clean it, because we've never taken a device off a warranty or charged anybody to fix it. If we're in there cleaning it every 6 months and a well breaks or something like that, which can happen in stormwater over time, we just handle that for them. We've never had a client get an NOV. I always knock on wood when I say that, because an inspector can write you a notice of violation just because he doesn't like the way you look. However, because we will show up and because we are available and we will discuss things with that inspector and we will make changes and we'll talk about how to improve the system or back watering out of a pond or whatever has to be done. they look at us a little different than a guy that drives in town with a set of brochures and might be another salesman 4 months from now or 5 months from now. No real loyalty to the jurisdiction, the owner, the contractor, or the engineer. You know, we're an engineer-based company. We back up what we sell. We have verified testing. We do honest design. And so we're not afraid to ask to present our resume and ask to be included on your next project. We actually have a printed resume. And that resume goes over the things I've kind of told you today. The green check mark you see on the bottom right down there, you can't say that we have been anything other than verified. Our claims were verified by the EPA. That doesn't mean that they're guaranteeing we'll work anyway, except we put out a device, they asked us what it would do, we told them, they verified it. And this is something relatively new. We've had it a while. This is our hybrid polisher. We call it that. If you look, if you're familiar with CrystalStream, on the front side, which is the left, you'll see a screening trash basket. Those of you who have older devices will notice we build them a little differently now, so this can be disassembled for top-down cleaning guys. You really can't see the baffles in the front, but they're there. There's a baffle up next to this center piece, which is the reservoir. Inside of that reservoir today, there's an internal, what we call periscope bypass. And as you know, we don't bypass overall, so we make this machine bigger. But in the back, what you can see on the right are two boxes. Now, these are called media boxes. There might be 6 of them in a really huge device. They hold filter media panels stacked, not just our coconut fiber filter. These do not have panels on them. You can see the expanded aluminum on the floor. But we can literally tailor the media, perlite, zeolite, activated charcoal, path shield to kill pathogens. And we're working on a project right now that has huge fecal coliform that we know we can get a 98% kill on. So we can go to a jurisdiction and say, what is your concern in this watershed? What's your TMDL? What do you need? And instead of going just a one-size canister, for example, fits all, we're going to use zeolite, perlite, and activated charcoal. Well, we tailor this machine. We can tailor this machine precisely into exactly what the needs of the site are. Should this be done everywhere? No. But in tough jurisdictions and places where you need to be sure, not just from getting a permit. You should be able to get a permit if we just put coconut fiber in the back, because then it would be the machine that we tested with EPA and others. But if you put these extra materials in and do the polishing, you should be able to convince people, and we can convince people, that we can actually improve and polish water beyond what was shown in our test. If you listen to me much, you know that we'd like to clean our devices, put our material into the landfills where they belong, and after we do that, we feel like we have done our job. And so we appreciate you guys being here today. I know there are some, let's see if I can get this back where I need it.